This is question 28 from the in-class application 6. This asks what the expected return and standard deviations of stocks A and B are. We got an expected return for stock A, a standard deviation of returns for stock A, expected return for stock B, standard deviation of returns for stock B. And the question is, what's the expected return and standard deviation of a portfolio that has 40% A and 60% B, and the correlation is 0.5. I have taken the liberty of calculating all of this already. Inputting all of this, so we're just going to move forward with the calculation. So the expected return is going to be, and this is the portfolio. Let me make sure that I type that. So notice we have an expected return for each of the stocks, and then we have an expected return for the portfolio, and this is the sum product of the weights and the expected returns. It does not matter what order you put the inputs into this equation. It just does 0.4 times 0.11 plus 0.6 times 0.13. Let's put that in percent terms. Okay. And let's just check. C 12.2, we got the right answer. Now, for the rest of the problem, we can't do what we did on the prior problems where we take a portfolio and get the different outcomes and the deviation from the mean for each of those. What we need to do is create a variance matrix. And the way that we do that is to take the standard deviation for stock A and square it. Take the standard deviation for stock B and square it. So here we have the correlation, and the correlation, let me just write this out. The correlation equals the covariance divided by the standard deviation for A times the standard deviation for B. We have the correlation. What we need to do is rearrange this equation to get the covariance. And the covariance is going to equal the correlation times the standard deviation of A times the standard deviation of B. This is a formula that was in your packet from last week, and it is very helpful for life in general, but for this in particular. So correlation times standard deviation times standard deviation. And since they're symmetric, we can do that across the diagonal. The last thing that we need to do is a weight matrix. And to do that, it's symmetric, so we can do that. The reason that we're multiplying the weights times themselves is because of the unique way that this calculation sort of works. So what we're doing here is we are looking, so the variance covariance matrix says you care what the variance is for the asset itself, but you also care about its interaction with the other assets. And so the weight matrix sort of helps us properly weight the variances. So for instance, this asset, asset A, will care about its weight here, but will also care about its covariances here because it has two possible relationships. The relationship of itself with asset B and asset B with itself. It's a little bit counterintuitive, and this to me is the hardest part of all these problems, but that's the way you have to do it. And so the portfolio variance matrix is just going to be these matrices times each other. The last two steps are to get the variance, which is going to be the sum of all of these, and the standard deviation for the portfolio is 60%. And we see the solution here. Let me make that a percent so we can talk about it. Okay, the next part of the question says calculate the standard deviation if the correlation coefficient is negative 0.05, and then it asks what does the correlation affect, how does it affect the standard deviation of the portfolio? Okay, so let's just do a chart over here. Correlation 0.5. I'm going to go down and do negative 0.5. When it's 0.5, it's 60%. Let's make it a negative. Oh, negative 0.5. When it's that, it's 42%. Let's make it 0. Let's make it 0.99. 67%. And then let's make it negative 0.99. Let's do 1 or 2 in the middle. 0.25. Okay, so if we look at these correlations, let me just make them yellow so we know to look over there. And we'll zoom in a little bit. It was 60% when our correlation was 50% or 0.5. When we did negative 0.5, it went down to 42%. And you can see like this is increasing. As our correlation increases, the standard deviation, which is the risk of the portfolio, increases. So what does this tell us? When the two assets are highly correlated, 0.99, they move almost 1 for 1, the risk of the portfolio is much higher. When they're negatively correlated, the risk of the portfolio is much lower. And why is that? Well, when good times come, one asset does well. When bad times come, another asset does equally well. Since we only have two, stock B, say, will pick up the slack. And so if they're negatively correlated, then you always have kind of an okay time. If they're positively correlated, then in good times, the portfolio does really well. In bad times, the portfolio just gets hammered, and there's no sort of insurance. So correlation tells you the insurance that the two assets provide, and that's why the negative 0.5 has such a low standard deviation, is that there's more insurance here because they're negatively correlated. When one does poorly, the other does well, and vice versa. And so that's kind of the message that you want to get out of this. The higher the correlation, the less benefit from diversification.